Okay, let's get started. So my name is Wayne Getz, and I'm a professor in environmental science policy and management. And my office is 5052 Valley Life Sciences building. I haven't set up my office hours yet, but I will. I usually do it on Wednesday afternoon. If anybody can't make that, then you just email me and I can set up an appointment at another time for you. This class is called Modeling and Management of Biological Resources, and there's a website at BSpace. Is anybody here who's been to the BSpace website? Anybody who hasn't? Wow, there's a whole lot of people who don't know what they did. So when I ask you a question, you've got to respond yes or no, okay? Because I can count. And so I like to sort of see, being a mathematician, I like to see the complement of those of people who are answering also going to answer to the negative. What I usually do is I put my lectures up in this form, kind of an outline, before class. And those of you who can't make it, this is also recorded. And so what's recorded is my voice and also the material that's on here. For part of the class, I will be using the overhead, but part of the class I'll teach on the board, so it will vary. But initially, I'll be teaching more on the overhead, and in the later half of the class more on the whiteboard. We have two GSIs for the class. So Colin Carlson over here and Eric Doherty. Who's taking the Friday? So Colin's going to take the Friday sessions in Mulford. So that's the Computer Lab 124 from 10 to 12. And Eric's going to take Monday 12 to 2. Now, obviously, you all know that this coming Monday, there's going to be no lab because it's a holiday. So there's going to be one tomorrow and one on Friday again. So it's not fair on all the Friday people. They kind of get a double lab before anybody else gets started. So what I'm going to do today is I'm going to introduce you to Nova and show you some of the stuff that I wouldn't show if we had the Monday lab, but we don't. If there's anybody here who's on the Friday but wants to come, sorry, who's on the Monday but wants to come to the Friday lab, feel free to do so. Are we finally out of chairs? Do you want to bring one in from, is there one outside or something? So the way classrooms work is the fire marshal says there can only be 50 people in this room, excluding me. So if I go, they don't care. And I'm allowed to have 10% more than that, so that's 55. What usually happens is we start with a big class like this, and then some students drop out. If you're on the wait list, I can assure you that within a couple of weeks, there'll be a place for you, because it's not a big wait list, and at least half a dozen or more students are going to drop out. So those of you who are really interested in taking this class, just keep coming, and I can guarantee that I'll get you into the class. Okay, so we have, at BSpace, we have a course outline, and I'll just go quickly through this outline so that those of you who are thinking whether you want to take this class or not can then decide based on the outline whether this really is for you. And this class is centered around two themes. The one theme is to give you a better background on how to build models using mathematical equations. Did you want to get a chair outside? Is there one outside that you can pull in? And to do that, I'm using a calculus textbook that I wrote with a professor up at UC Davis and another professor from one of the community colleges, Carl Smith. And it's available at the bookstore. It's called Calculus for the Life Sciences. Now, a lot of you have done, everybody here should have done a calculus course and had an introduction to integral and differential calculus. So what I'm assuming is that you don't really remember the stuff. So who took a course but doesn't remember it? Okay, thank you, that's helpful. So this book, because of the examples that we've got, the examples are part of the modeling aspect of the class. Teaching you calculus is not, but if you go through the book, all the stuff you need to learn or to revise your calculus is going to be in there, and it's up to you just to read a little bit of background. And from the flavor of my lecture today, you'll see what I mean. I'm not going to ask you to integrate a trigonometric function in the exam. I promise you that. The simplest thing you'll have to do is some simple algebraic stuff, and that'll be clear. Which brings me to the second theme of the class. The second theme of the class is that we want to teach you how to use computers to simulate models. So are you guys at the back there okay? Yeah, I'm sorry about this. As I said, in a couple of weeks, there'll be plenty of space. If you want to try and get a chair outside, you're welcome to do so. Just don't tell the fire marshal that I said you could do it. So this software is really a very neat software package, and it's a very powerful software package, but it's been designed so that you can very simply learn to simulate models, dynamical systems models, and the kind of models that we talk about in this class, very simply. You don't have to know how to do any coding. So this is kind of a code-free approach to building models based on code. So it's all done through graphical elements. So I'll bring up the website, and there's a lot of interesting stuff at the website, and my colleagues and I have used these to run workshops, one workshop in Israel, this is at a high school where we collaborated with a teacher doing a MOOC there on modeling and epidemiology. We did one at Oberlin. We've also just recently done one in South Africa. If you go to this website and you open it up and you go to downloads, you'll see that you can download the software onto your own machine, Mac or Windows, or running Linux if you want. The latest build of the software, which you don't need to worry about, is over here, just because we are working on the software and we are improving it all the time. But what's important for you is the opportunity to download it. You have to go through the registration process, but the software is free. Then you can go to tutorials, and there's getting to know the Nova interface. And there's also then, after you've got to know the Nova interface, it's a 10-minute introduction. There's one on population models, simple population models. And so when you run these, you'll hear a voice that might become familiar to you, and it belongs to Andy Lyons, who was at one time a PhD student, and now is teaching as a postdoctoral instructor at Stanford. And he's a really great teacher, and I'll persuade him to come into the class, and then you can all get his autograph. He's, let's see, okay, so this is taking...
Okay, welcome to tutorial 2, and getting started.
And then
it's basically the number of, you can also click over here to add the...
Et cetera, et cetera. You can run this, I think, at 1.5 speed if it's a little slow.
And now we see a similar kind of shape, but before, the population...
So, and there's also a Nova guide, which has got all the information, but really, hopefully you won't even have to use this. We're going to tell you enough so that everything you need to know will come through my lectures and through the lab. And as I said, it's going to be a fun class because it's fun to play around with models. Everybody believe that? And I don't mean that that's the double entendre meaning either. So what we do in this course is I'll introduce you to basic difference and differential equations. And then we'll talk about various kinds of models. So, for example, we'll talk about models that people use in genetics to look at the frequency with which genes that confer resistance to pesticides or drugs can be selected for in populations. These are actually very simple models, and these models also appear in the textbook that you'll be using. So these are the different sections of the textbook that you read to go along with this. Some of you might not need to read the textbook in the early parts because that's basic review of some calculus that you might need. So SSG stands for Schreiber, Smith, and Getz. And then there'll also be these H1s, H2s, which are handouts that I'll give you. We'll go on to talk about host parasitoid models. Host parasitoid models. How many of you have heard of biological control? So in agriculture, where you introduce insect predators and pests to control other insects or arthropods, there's simple models that do that. We'll also talk about forestry management, the optimal rotation problem, and the Faustman problem, because half this class are environmental economics, so this is very geared towards looking at natural resource management. We'll talk a lot about harvesting theory and fisheries models, and we'll get on to life table models and age structure models. So these are models where you analyze a population from the point of view of its age structure, and these sorts of models have been used either to manage resources where age structure is important, or to analyze different sorts of things like the extinction of populations, and we'll look at it in that context. Then we'll get into slightly more complex differential equation models that are used to model population interactions, and the two processes that we'll begin to focus on are what are called prey-predator models, consumer resource models, and also competition models, both from an ecological and an economic point of view. And then we'll get into stochastic simulations. So we'll understand that if you look at a population that's rather small, you're not able to predict exactly what's going to happen because you only know the probability that an individual may die, but you don't know for certain how many individuals are going to die in a small population over a certain point in time. So you have to do simulations that take that kind of stochasticity into account. And then population viability analysis with its application to conservation biology, and then some other nonlinear models that provide us insights into how neurons fire and how genes switch on and switch off, just very simple models from biophysics. And so that covers the course, but the main purpose of this course is to teach you a way of thinking and to give you the skill of being able to build models using our software. Are there any questions so far? Yeah? The reading. No, the readings are not due. You don't. The only thing that's due are the work sets. Oh, no, it's anytime. You can come to class ignorant and just listen, and hopefully I'll make you smarter by the end of the class if you don't go to sleep. Or you can read ahead if that helps you. It's your choice. Or you don't have to come to my lectures. If you find them awfully boring. So some students who've done the best in the class didn't come to lectures because they were smart enough not to waste their time here. But with topics like this, the lectures are usually pretty useful. And I try to kind of elaborate and give a... So I don't like to go over the stuff in class that you can read in the book. And sort of, I don't want to work too much math on the board, because that's really boring. You can do that in your own time at home. I like to sort of have a more general discussion about the philosophy of models, how we use models, the different applications and things like that. So that's what the class is about. And I like it if you come and ask lots of questions. However, the work sets are the two ways that I can find out whether you're learning stuff in my class or whether you really know stuff. There's a midterm and a final. And the midterm, which is going to be held on October the 9th, and then the final in exam group 17. And I virtually tell you almost all of what's going to be in there. And you can speak to students from previous classes and they'll tell you this is true. Despite that, I guess some students don't do so well. So I usually wonder what they're thinking. Like if I say to you something's going to be on the exam, it's not very smart not to prepare for that. But of course, it's not about the grade. It's about being able to do the stuff. And so usually these two, the midterm and the final, will cover the kinds of models in a more theoretical sense that we discuss in class. But the work sets themselves are the practical part of the course. And in the work sets, you do two things. You mainly build models and run them, and then there's a little bit of things like plotting graphs and interpreting what they may mean, and a minimal amount of algebra as well. The work sets, each work set is out of 25, and you'll get 10 of them. I'm very strict about late work sets, and I'm very lenient if you have a good excuse. So if you're going to bring a work set in late, you're going to get 0 for it, and you're going to have to do 9 out of 10 of these work sets graded to a minimum of 10 points out of 25 for the work set. But you'll only get credit for that work set to your final grade if it's added in on time. However, if you let me know you've got a problem, and you have a good reason why you can't make it, then I'll certainly negotiate a new date with you. But the important thing is to really keep up with the class. So that's why I don't want to have people kind of getting behind on the work sets, because you're not going to keep up with the class and then you're not going to learn as well. So it's only for extraordinary things, like if you've been ill or something. But typically not if your mother's visiting from out of town. Then the total grade is out of 500, so the midterm is 100, and the final is 150. You get a grade of 5, you get 500 points, and sometimes you give bonus points. And I divide by 5 to get a percent. Now to get an A+, you have to get 90 over 90. To get an A, you only have to get over 80. To get a C, you only have to get over 656. So that may seem really easy, but actually, some students manage not to do that. I usually have only maybe 2 or 3 students who could get C's or worse, and I give lots of B pluses, A minuses, and even 25% of the class may get an A. But to get an A+, maybe only 2 or 3 of the best students in the class will make that. There's some other reference texts which are background reading if you want. The books are in the library. I haven't put them on. I haven't asked them to put them on 2-hour hold because there's nothing that important in them. It's just for general background reading should you desire to get some. Okay, so any questions about the schedule? Okay. Yeah?
So was that pretty much the problem from the textbook?
No. So the work sets are really, there may be some problems in the textbook that come from the work set, and some that are a little bit more complicated than you'll find in the textbook. So this textbook is for, lower division, and you're upper division, so you've got to do harder stuff. Just kidding. Okay. Not kidding. Am I kidding or am I not kidding? Who thinks I'm kidding? Good guy. Okay, so here's a typical work set. No, it's not a typical work set, it's your first work set. In this first work set, there's a very simple model, and I'm going to talk about this model today, and this model will be discussed in the calculus textbook, and it's called a difference equation model, and I'll talk a little bit about difference equation models in a minute. And here's a differential equation model, and so you'll learn the difference between difference equation models and generating sequences of numbers, and differential equation models and generating continuous time output that typically we call a trajectory. Then here's a slightly more complicated version of this model where R itself over here is a little more elaborate, so there you see the x of t term. And then what's happened is I've taken the R and made it a little more complicated and involving x. So I'll talk all about these sorts of things. And then I ask you to plot this and use your favorite graphing program or Excel. So just because there's something there doesn't mean you use Nova to solve it. Nova's there to build continuous models that change with time. I ask you to evaluate the derivative of this function. That means you have to take the derivative of this function. This is for a small amount. And there's some questions here, and then I say, okay, make sure that when you use Nova, and when you hand this in, you generate a PDF. You can build your PDF. How many of you use something like MS Word and can generate, let's say, graphs? How many can generate graphs in Excel and then paste them into your MS Word? So that's the sort of thing. If you don't know how to do that, you're going to learn how to do that in this class. And I can't teach you how to use MS Word and generate graphs in Excel. But we can, if you're struggling when we come around in the lab, we might be able to give you some advice on doing things. You might also have your own graphing program. All these programs generate images. You can save things from your program as a JPEG file or PNG file or some other suitable format, and then you just drag and drop it into your Word document. Is anybody who uses anything other than Microsoft Word for building their documents? Wow. So we've all drunk the Kool-Aid, except for one guy. Fine, whatever. You just generate the PDF. So I don't care what you use. I've even had people use things like LaTeX or HTML if you're sophisticated, but oh God. Okay, so I like Apple, but they've got these rinky-dink things that fall out. But that's because they're making everything so small. Okay, so is it clear about the work sets? Okay, and the other big no. So yes, work together, help each other. That's important. In the future, in real life, people are effective in teams, and they work together. But in this class, you're welcome to work together in a team, but each one of you has to produce your own PDF, and it has to look unique. And you can't just copy stuff. So you can help each other. You can help each other build things, but when you do the runs, it's your set of runs, and you don't have a shared document in the end. And the only reason I do that here is because I don't know if there's a free rider or a freeloader. And I know, like, in a couple of people working together, there may be a freeloader, and you're not supposed to rat on your friends or say anything bad, and so you tolerate it, and then you beat the guy up somewhere else. But then I don't know if they've really done the class, and I don't want to give them a passing grade if they haven't mastered the material. So the only way I know that you've mastered the material is if you give me your own PDF that I have seen that you created yourself. But it's fine to sit down and work together with others, to problem solve with others, but when it comes to the final report, each one of you must have your own report. Even though I say this now, people sometimes ignore it. And I'm always amazed how students think that the GSIs are not very smart, that they're not going to see this. But when I go to the smartest GSIs here in ESPM, when they go through the stuff and they say, this looks familiar, and then they go and check, and I have to give both parties 0. So I can't sit there listening to who copied from whom and who said what. If that happens, unless you can prove that your work was stolen by somebody else and then copied, I have to give both 0. So please make sure that that doesn't happen. Okay, that's about work sets. Anything else? Okay. So we've got the lab meetings, the class text, and handouts. So if you go back to your elementary math and calculus, you learned about what are called exponential functions. Does anybody want to give me a definition of, well, firstly, what is a function? Yeah? Okay, wow, thanks. Okay, so not one and only one, but there's, for every x, there's a unique value of y. And if it's one and only one, then it's monotonic or it's one-to-one. But yeah, that's great. What is then, so a function generally looks like, I never know which board to start on. I should have been able to figure this out in 20 years. What's the probability that I'm going to cover a board if I start on it? Anybody know?